Okay. Good morning, everybody. So let's get started right away. So the main motivation of this talk is what I like to call the temperature crisis. And essentially, as we will see in the next few slides, this is a multifaceted problem. And one of them is, one of the facets is summarized in this plot, which essentially shows that over time the increasing power density of various types of IT equipment, ranging from servers to network infrastructure to personal computers. So over time the temperature has, the power density has been steadily increasing, and actually you see this change in slope. That means that overall the industry collectively, the IT industry collectively, is trying to keep this growth under a reasonable rate. And the main reason is, as we will see, the temperature increase that this power density growth is imposing on the systems and on the devices. It's clear that this is a problem that is at the chip level, but it is also at a very multi-scale problem. So it is at the chip component level, it percolates to the blade. So these are all thermal diagrams with color coded showing hot spots and cool spots in various pieces of IT equipment. So this is a board. You can see there is a very significant spatial thermal gradients. And we can scale it up at the rack level. And again, you can see here quite clear non-uniformities in temperature and even at the entire room and data center level. And again, you see that we have problems here. So overall, the main problem, if we take it from the bottom, if we take it from the Moore's law viewpoint, from the silicon integration viewpoint, is what I like to call the thermal wall. So in early days, we had, once upon a time, we had very nice picture, a single core scaling up very nicely in terms of frequency. Then the power wall was hit, and speed scaling roughly stopped. And the people started to put multiple cores on a chip. This is all very nice, and they say, okay, if it works for 4, then we can work for 8, and then for 16, and this is actually happening very fast. And then you hit the other wall. And the other wall is basically that your total chip power is actually exceeding the thermal design power, which is essentially the power that you can dissipate through the package and into the environment at a reasonable rate. And this is what is called the thermal design power. Now, we can design chips today, and most of the chips that are today in the market actually are designed to be above their thermal design power. In other words, you can find a way to take these chips into burning by tricking them. If you essentially make some strange and nasty tricks, you could even take the system into burning. And so if we project this problem in future technologies, then we see that essentially it boils down to the fact that you can put a lot of transistor on the silicon, but since you are pinned against the thermal wall, you will not be able to power them at their maximum capability level all the time, and only a relatively small fraction of the chip can be powered at any given time, and this has been called dark silicon. Okay, so only part of your silicon can be lighted up, do something, and the rest has to be dark. And so one may think that this is a problem for servers, for ultra high performance computers, but this is in fact not the case. And actually where dark silicon is biting very badly is mobile platforms, because you cannot afford, for cost reasons, to go into very expensive cooling solutions. You cannot afford ventilation, and you cannot afford large form factors. So essentially you are constrained by the form factor of the device to have, and the cost of the device to have limited cooling capabilities, and so here is where the problem really bites at you. This is only one facet of the problem. The rest is, even if your system doesn't go into thermal shutdown or thermal runaway, you have reliability issues. If your system has to have a relatively long lifetime, as we have seen, it's going to operate, because of the issues that we described before, at a quite high temperature, which is going to be dependent of the voltage and, of course, of the requirements that you put into the system in terms of workload. So you will have a temperature which is going to be fluctuating over time, but going to be quite high over time. And physics has highlighted many semiconductor failure mechanisms that I'm not going to highlight and describe here, but there are many of them. And essentially, all of them become exponentially worse with higher temperature. And so this boils down to this type of effect that you can see from statistics of component failures. And if you do some diagnosis, you would see that many IT components would fail for several reasons, like being wet or dust or vibration, but by far the biggest cause of failure in computing equipment is high temperature. And this is not thermal runaway, it's just aging. Rapid aging that shortens the life of the device until it breaks down, not dramatically like in fire, but just, it fails, okay, with logical failures. And this is because it has aged very rapidly because of high temperature. So essentially the idea is that your reliability, which is 1 over the probability of failure, goes down over time, and actually with temperature, and which is of course high when you power the chip at a high frequency and voltage, your reliability goes down rapidly, and then it will actually violate your lifetime target, because at the lifetime you will have a much lower reliability than what you would desire. So a simple solution is to say, well, let's go operate the system slower and at a lower voltage, so the temperature will go down, and then we recover the reliability. But of course this will kill the performance, so you have to do this in some intelligent way. But to summarize this slide, remember that temperature is a problem also when you don't burn things, but you slowly age them. Finally, one could say, okay, now everybody is saying that we should worry about temperature, so let's push the idea of actually going to cool silicon down, and let's go to dim silicon. What does it mean? Since high voltage, high operation voltage, and high frequency are a problem, then let's push into near threshold. So let's make systems that actually are ultra low power, because they operate at a slower frequency, maybe with many more cores, but at a lower frequency, so they are safe from self-heating. And then the die temperature will be, we are going back into the green. So it's going to be system temperature of the system, more or less the same as the temperature of the ambient. And since the dissipation rate is going down, we are not going to have big thermal gradients across the chip. So everything is going to be nice. And this is just because we are lowering the voltage supply and the frequency very close to the threshold. And so this is, and we are going to be extremely energy efficient with our devices. That's great. Unfortunately, there is a temperature we don't have control on so far, which is ambient temperature. Okay, so this is actually showing to you the what happens over a year in Washington. Okay, actually Waterloo Station, weather station, and actually you can see that this is typical, continental weather with fluctuations on the cold side, with fluctuations that go from below zero very significantly to well above 30 degrees, and this is where we live in Europe, and in Bologna is like that. Maybe not up to -30, but we go to up to 40 in the summer. So, and as you know, the critical path delay of the devices is highly influenced by the temperature, and indeed this influence is magnified by a factor of 10 when you go near to the threshold voltage. So in other words, temperature in this case will bite at you, because if your chip is put into different environments, its actually frequency of operation will change dramatically because of the fact that it is so close to the threshold voltage. So even for cool silicon, there is no escape to worry from worrying about the temperature during the operation of our device. So in the rest of the presentation, I'm going to actually discuss how we can do dynamic temperature management. In other words, how I will not talk too much about designing silicon, but how to use the silicon. I will have something about design, but very little. And so given a silicon, how we can manage it to deal with the temperature. And I will differentiate between hot silicon, warm silicon, and the cool silicon. And I will show techniques that apply to the hot silicon, to the warm silicon, and to the cool silicon, and show the analogies and differences, and also look at where we are going in all these things. And overall, the big picture from the methodological viewpoint is actually, you will see there are some regularity in this picture. So essentially, we will have to see the system as a distributed state and multi-input, multi-output control system, which provides information from various types of on-chip sensors or on-board sensors. We talk about the board. And this is going to be a multiplicity of sensors which are going to provide an information about the state of the system. That is going to be thermal state of the system. It's going to be not completely observable, but only observable through these non-ideal sensors with noise, errors, and so on. And then we'll have a controller, and the controller will have to estimate the thermal state of the system, which is only partially measured. And it will have to try to operate the system according to some performance requirements. And I assume that the performance requirement is provided, for example, in terms of a request of operating frequency from a higher level scheduling, workload assignment, and controller that we have on top of the temperature and thermal controller. So this is the composition is quite artificial if you want, but since most of the things I'm going to describe today is in the area of temperature control, I decided to partition the control problem into decisions about the workload, and then how you make sure that the workload can be executed as faithfully as possible to the requests without violating temperature constraints and keeping into account the temperature variations. Okay. Actually, this problem, you could see it all together, and I have some hints on that, but most of the focus is going to be on this. Okay? So, let's discuss about hot silicon. So, the first part of this presentation, we are going to go into model predictive thermal control for hot silicon. So, this is an area where I work for already several years. 2 years ago, I gave a presentation exactly on this topic here at the Artist Summer School, and I would like not to repeat what I said, but I have to give you an overview of where we start from, so because not everybody was present 2 years ago, so let's go into the basics. So, basics is that we are going to apply this on, of course, on hot chips. So we are going to use as an example the Intel single chip cloud computer, which is a 48 core single chip. And it has, in terms of control, you can control its voltage and operating frequency on quite a wide range between 0.5 gigahertz and 1.2, 1.3 gigahertz. And then these type of frequencies, this whole system has actually a very significant range of power consumption. As you can see, it goes from 0.25 watts to 200 watts. So it is definitely a hot silicon guy. Huh? Okay, so this is very near to the limit that you would afford for a chip, unless you go to extremely exotic cooling. So this is the overall architecture, and this is actually a perfect example, actually quite extreme example compared to chips that are in the market today, even by Intel, on how fine-grained you can make a control and the monitoring. So here you can decide the operating points in terms of frequency for each core, in terms of voltage for cap pairs, of course. And actually, you have quite a fine-grained temperature sensing capability because you have a couple of temperature sensors in each of these tiles. So overall, this chip features around 100 temperature sensors on a single die. Okay, and this is not what Intel is doing in products today. We will see when we will talk about supercomputers, much less is exposed today. But this is like an extreme chip representing where chips will go in terms of state observability in the near future. So the general architecture then is for a thermal controller is following against the template that I described before. We have all our monitoring, which is monitoring not only the temperature but also the workload. And we will use the workload as a proxy for power consumption because there is no direct measurements of per core power consumption. We will not have it, but we can use the workload through a nonlinear model to estimate the power consumption per core. There is a trend to also have power measurements on the chip, but this is not even available today in research chips, but it's coming. So today we are going to use a workload through a nonlinear model as a proxy for power. And then we have the control. Power state control, so this is the VFS, and C-state control, which is power gating. And we have all our applications that will be allocated on the various CPUs, and the controller will decide upon the frequencies at which these guys will have to be operated, depending on the workload, and depending, of course, on the thermal state. And there are a lot of approaches here. The most common ones that are used in products in Intel are threshold-based. So you have a panic threshold, a attention threshold, and and wake-up threshold in terms of temperatures. When you have panic threshold, you shut down everything. When you have a problematic threshold, you start moving things around. And when you have attention threshold, maybe you want to do some proactive power management. And the proactive power management is basically something that is more than waiting for a threshold to be hit, but is actually using control theory to monitor the workload and to try to apply smooth control techniques so that you don't have these drastic reactive control actions that may come too late. And when they come, they disrupt the operation of the system in terms of capability, functionality, and workload. So the idea, the approach that we developed in the last 3-4 years is essentially that you have this energy controller that is the workload, takes the workload and requires a given frequency to the cores. I'm not going to talk about this one. And then you have the thermal control. And the thermal control takes also the thermal state of the system into account, the request in terms of performance, and decides which type of frequency can give given this constraint and given this request. And the target and the model that we are going to use is the so-called model predictive control. And the idea of the model predictive control is that actually within your control loop here, your policy will embed a thermal model of the system. So you will have to have a thermal model of the system, time domain, state-based thermal model that will actually help you in making the decision. And you actually perform optimization. So knowing the model, knowing the requests coming, knowing the state of the system, you make an optimal decision on the future horizon set of actions, and the actions that this controller implement are basically frequency and power and voltage requests to the actuation of the system. So you define an optimal trajectory of operating points based on your requirement and based on the thermal trajectory, the thermal state of the system that you estimated and you know through a thermal model what will happen in the future. And this is why it is called model predictive, because it uses a thermal model of the system to predict what is going to happen in the future. Okay. So this type of, just one word about one important point. A power model of the system, a thermal model of the system requires as an input the power consumption, because thermal model takes power and turns it into temperature.
So we need to know how much your cores will dissipate, but the core won't tell you. So basically you have to use the workload of the cores as a proxy for the power. And to do that, you have to do a lot of tricks, linear fitting, characterization runs. So this is a very well-known art. I'm not going to spend a lot of time just to tell you that this is actually nonlinear function, and this you have to remember, because when you want to do control theory, you would like to have everything linear, and when there is something nonlinear, there may be trouble, okay? But anyway, so this model is something like that, which is essentially showing in terms of what is going to be the capability of your system to do clock CPI, clock per instruction, and what is the power as a function of the workload of the system. And so you see this is a nonlinear function, and you can fit it quite reasonably with some exponential and polynomial approximation. And this is your function that given the CPI, so how much the system is busy, clock per instruction will give you the power. Okay? So take home point, it is nonlinear. Now, let's go into the thermal model then. We have this nonlinear power model. Given what the system is doing and given what the frequency of the system is, we'll tell you what is the power that actually the core is burning, is dissipating because of the workload. And then it goes into the thermal model as an input into the thermal model. And the thermal model is a state-based model where the state is essentially the temperature. And this is the current temperature, and this is the future temperature, and this is the power, which is the input of your linear model. And these are the two matrices that are the matrices, the A and B matrices of a state-based linear model that actually describe the evolution over time of the temperature as a function of the power and of the past temperatures. Okay, so this is a discretized version. You will have, a derivative here in the continuous time, but this is a discretized version. And the reason why I use x here and not t, because these actually are temperatures, is that not all the temperatures are observable. So you only have the temperatures where your sensors are. And this is basically expressed by this matrix C, which is basically telling you the only part of your temperatures on the chip are observable, and this C is basically the observation matrix, what is put outside that you can measure. So essentially this is what you are going to be available at your controller, not this one, so you will have to estimate this one. This is a typical problem of state estimation, okay? Good. So given that setup, the question is how large are these matrices and how sparse they are. And in fact, the most important one is the A matrix, because the A matrix is the one that correlates the past history, thermal histories of the system with the future thermal history of the system. And it turns out that heat flow is quite well behaved. Heat doesn't jump all over the place. It's not a quantum process. It's a continuous process. So the idea is essentially that it is governed by a partial differential equation, which is Fourier's law. And this partial differential equation can be discretized over time. And actually the basic idea is that this essentially shows what happens in a system. This is a discretized version of a heat wave. So if you have a point source dissipating heat in one point, the temperature effect of this heat source will actually dissipate like a wave in a pool of water when you throw a stone in the wave, in the pool of water. So you will see this heat wave going further and further away from the point source in time. Okay? Now, so if you discretize your system at the fine enough frequency, so if you sample your system at a fine enough frequency, then your A matrix will become sparse. Why? Because the temperature in one corner of the chip will not directly influence the temperature in the other corner of the chip if you sample the system fast enough. Actually, the temperature of one corner of the chip will influence the temperature in the other corner over a set of state propagation intervals. And so the finer you sample the matrix, the more sparse it is. So, and how fine you should sample the matrix? This is the question. And in fact, if you sample it on the few milliseconds, tens of millisecond time scale, your actual thermal neighborhood, which decides how sparse is your matrix, how are the non-zero elements close around the diagonal, is actually quite small. Okay? And this, please keep it in mind, because it is a very good news for us. We will see it, because it means that you can do distributed control. And this is coming now. Okay? So then how complex is the model? How many poles and zeros there are in this thermal model? And in fact, it turns out it is reasonable, simple, but not too simple. In fact, there is a second order local model. And essentially, it is basically saying that there is not a single pole, but there are two important poles in the system. So this has some implication, but it's not a terrible system to control. We know how to keep it under control quite nicely. So overall, the thermal control problem, casted, as we said, is a multi-input, multi-output control problem. And its complexity is superlinear, very significantly superlinear in the number of inputs and outputs. Remember, the number of inputs are all the temperatures that you sample, and also the ones that you don't sample, but you can estimate through a state estimator. And the output is the frequencies that you control in the system. Okay, so if you have many of these and many of these, your complexity of your controller will blow up non-linearly. And actually, if you do model predictive control, it will explode exponentially. So you do need, if you have a system that has 100 state variables and 50 controlled variables, you need to go to something hierarchical, because simply computing an optimal control on this scale will take too much time, and you will not be able to do it in real time. Remember, this is a controller that works in real time. You cannot just spend 1 hour optimizing, finding the optimal trajectory, because you need to do this in a few milliseconds. This is the time of your control decisions. And so essentially you discretize your controller as well, and the idea is that you exploit the fact that the heat wave is, the A matrix is quite sparse, to be able to do a local control. And the local control is basically a set of interactive thermal controllers. Each one of the controllers is dedicated on a core, and will actually control the frequency of the core. So it's going to have one input in workload, and we're going to have one controlled variable. And and in terms of information, actually, it will get the information on the neighbor nodes. So the state is going to be observable for the neighbor nodes. So it will have a local model, and the information will propagate between the various controllers through the neighbor temperature information. And each controller in this scheme will make its optimal decisions based on the information about the nearest neighbors and the information about the local workload. So without going too much into details, the model predictive controls, as I said, has these nonlinear functions at the input and at the output, and this is the nonlinear function that takes the CPI and the frequency to know what is the power. Remember that the power is the input of the control, so you need to have this. And then it takes the information about the state, observable state, which are the temperatures. It has a state observer to actually give you the information about temperatures that you don't observe directly through sensors. And then based on this, it will implement a online optimizer, which in this case is very simple, and compute what is the power. And the power is not what actually your control variable, but given this nonlinear function, given a power, desire the power for the future, you can invert this nonlinear function and get the frequency. So basically you will set the frequency through this nonlinear function to the system. This is the way it works. So I'm going to just skip equations here, because I think the idea is what is important to you. We have plenty of publications on this, and you can refer to the publication if you want to see the math. Now, if you do this on simulators, and actually more recently we actually are doing this on real hardware, but the results are quite consistent, what you will see is this plot show a few interesting things. So this plot shows a few benchmarks. So these are different workloads on the SCC machine, and actually you will see that we are comparing on a small scale, so on a relatively small number of cores. So we are comparing what happens with the centralized controller and our distributed solution. So we have various types of centralized controllers. These are centralized controller, yellow and blue are centralized controller with a simpler, very simple model of the thermal system. So to make the matrix A smaller, we make a simpler model so that we hope that the centralized controller will handle the system. And here is we are actually using a linear version of the power versus frequency function. So these are two approximations for the centralized controller. And actually, this is the full-fledged centralized controller with the complex model and complex nonlinear function between power and frequency, and this is the distributed controller. And actually, this is lower is better because this is your maximum temperature overshoot, which is what is the maximum number of degrees you went about your threshold, your constraint in your thermal controller. And of course, if it's lower, it's better because it means that you did not overshoot. And in fact, it shows that the green column, which is the distributed controller, is doing indistinguishably as well as the centralized controller, while if you oversimplify the thermal model, you enter into very large errors. And then here is for how much time you actually violate the bound, and even if you violate for a fraction of the degree, for how much time you violate. And as you can see, the two approximate centralized controller do very badly, and the distributed control does almost as well as the centralized controller. So actually this is very good news because it means that for this type of systems, distributed control works very well. Now the question is, can you implement this apparently complex distributed controller even if it is distributed in such a way that it will run online without overloading the system just to compute the control? And the answer is yes. It looks complicated, but it is actually quite simple. It can even be computed analytically. I'm not going to go into the details, but is using the theory of explicit model predictive controllers. And the basic idea is that you can make your control algorithm run in just a few microseconds on the cores that you are controlling. So the core is computing its own control sequence. And since your sample time for the execution of a controller is in the order of several milliseconds, there are 0.3% to 3% load, which is actually what you expect from a controller. It should not perturb too much the execution of your system. And so this is good news. This means that it's not only nice from the numerical viewpoint, but it is practical. Now, there are a few issues, and one of the main issues is who gives you the model, okay, the thermal model. You go to Intel and you ask, please give me the thermal model of the chip. You will get a flat line. Nobody will answer to you, okay? There are many reasons. They don't want to do because there are, some dirty secrets in thermals. But also they cannot, because your thermal model is influenced also by the thermal environment of your system. If you put your rack onto a wall, or if you put it in the center of the room, your thermal environment changes. So essentially, the chip manufacturer doesn't have the full information to tell you the thermal model of your chip, because the thermal model is somehow influenced by the way the chip is packaged, the heat, how the heat is propagated into the board, how the cooling works, and so on. So there is no way to get from scratch a thermal model. So as you know, people in control theory have dealt with this problem for many, many years. This is called system identification. Please.
In the concept, you refer to Fourier equations, okay? And it was your main concept to construct the mathematical model and relations between the power and observe temperature by sensor and the desired temperature. Okay, this Fourier law is applicable only for heat transfer by conduction. But in reality, you know, as you gave some example, it's not true. You cannot model the temperature distribution by Fourier law only.
Oh yes, you mean externally, out of the chip, because you have radiation and all these type of things. But the main dominant behavior within the chip is heat transfer by conduction, not by radiations and things like that.
99% or 20% or 50%?
All the measurements you have done show that is really, really close. So I would say 99% in the chip.
But what you measured just the surface temperature by sensors. These results doesn't show.
Oh yeah. It is also measured not by us, but there are many groups. It's a very wide field. We are not doing this alone, but a lot of people do it with thermal cameras, where they're actually looking at very detailed surface of the chip. And so it's quite a large community that is doing this type of analysis. Okay, so it's not only measuring some thermal sensors, but there are people that do thermal analysis by taking the lid off and looking with thermal cameras with a very high resolution.
You think if we model it by thermal conduction, it's enough?
In the chip.
In the chip.
Outside, things are more complicated. Because outside you have radiation, you have forced ventilation, you have other things. So it's more complicated outside.
Okay, means that we cannot eliminate it.
You mean eliminate what?
Eliminate the heat transfer by convection, for example.
No. I mean,
we cannot.
It will stay there. Okay, we will use approximate compact models.
Means that we cannot consider only the Fourier law in thermal model.
In the whole spectrum of thermal models,
no, just
definitely
for chip.
Not. On the chip.
On the chip, you cannot. We cannot apply only the Fourier law. Should be combined with the environment. This is the physics of the heat transfer.
Yes. So they are not totally decoupled. Okay, so you cannot decouple exactly. You cannot decouple them. But here I'm looking at the thermal model in the chip, and when you go outside the chip, I will have some thermal coupling coefficients that I will use. So it's approximated, but it's not isolated. It's not in a heat bath. This one. Okay. So you will have some thermal coupling coefficient with the external world of the chip, like thermal resistance, which could be nonlinear, and we will see some example of that.
And short, how many % of the electrical power you convert to heat? 100%, 80%, 70%? You have the power in your transfer function.
Yes.
So and you consider all this electric power as generated heat in chip?
The chip, the power that goes in,
yes,
becomes heat. Yes.
100%.
Yes. Sometimes it does something useful. Sometimes it does nothing useful. So you don't see it as a computation because it's dropping on some resistances and so on. But yes, it ultimately is not stored anywhere.
Okay. Thank you.
Okay. So.
I have a question, computational question.
Yes.
Just what is the horizon in time step that you look forward in the model predictive control?
Very short horizon. So this is actually all the model predictive controller that we apply is a couple of steps forward. Okay, so because we are actually using rolling horizon, so in the next step you will see a couple of steps forward. Okay. So we don't use it for very long predictors, and the problem is not so much the thermal model, is the workload, because your workload will change very dramatically over time. So if you try to make a prediction too far in your time horizon, your input is probably going to have a lot of error. So if you know that you have a constant workload for a very long time, then you may have a longer time horizon. You may even use a steady state thermal model.
Right, so that's why you can do it quickly also.
Yes, of course, yes. So the two easy cases are short horizon and asymptotic. The middle is where the complexity grows up. Okay, so you go to system identification here, and the basic idea of system identification is that you would put the system with a known workload, which will try to excite all the poles in all your model in a nice way. And then you use some standard state space identification techniques to come up with this model. So the idea is that the system should be put into model identification mode sometimes, not every second, but every week or so, and then go through this and create a thermal model. And then you can also add some calibration in the field, so some model tuning in the field in such a way that you keep your thermal model aligned with what is happening in the system. And there are other reasons. There are several reasons why you want to have in-field self-calibration. And one is the fact that the power model is not truly linear over a very range. The thermal model is not truly linear over a very wide range of temperatures, because your power consumption of your devices will change in a non-linear way if your temperature moves on a very large range. So you need this type of in-field self-calibration. So this is where we are. The techniques in this area. So we actually developed and published a distributed model learning technique that looks into learns a local model. So it's scalable, similarly to the control algorithm, and so this works reasonably, but when you apply it in practice, you will see that there are some very serious problems in the practical applicability of these techniques. It works very well on MATLAB. And the reason is that the sensors are very, very bad and very, very noisy. Okay, so you have a lot of sensor noise here. And actually in SCC, the sensors are almost unusable because they are uncalibrated. So, this is actually showing what is the various sensors, what are the various sensors in terms of temperature producing on the thermal, on the chip. So these are on various positions of the chip, and you see it's all over. And you say, well, maybe it's because of workload. Well, actually it is not, because this is when actually the system is quite uniform, and you see a lot of these non-uniformities. When the system has uniform workload, you would expect a reasonably uniform temperature, and you will actually see a lot of these non-uniformities, which actually point out that the sensor is badly calibrated and they don't match each other. So there is quite a lot of work to try to get useful data out of the sensors, and even if you work a lot and you try and you cancel the bias due to lack of calibration, still there is a lot of noise, because these sensors are based on ring oscillators that measure a frequency, and so there is a lot of intrinsic noise in the measure mechanism that is used to actually provide you the temperature value.
Excuse me, this is capacitance-based or impedance-based sensor?
These are ring oscillators. So the ring oscillator, since the temperature of the inverter is influencing the switching speed of the inverter, you put them in a ring, you measure the frequency, and the frequency has a relationship with the temperature. So there is quite a lot of noise, and even if you calibrate, and then you have to have a learning system identification procedure that is actually sensitive to this type of noise. And this is not a simple problem, because this noise is on the output. It's called output noise. And then there is a lot of new theory that you have to apply. And this is actually the paper that we published in Day 2013, which addresses this problem. Okay? But this is actually where we are. And this actually is working quite well, but there is more complication coming up. So in the last few minutes of this morning, I will try to give you some views on more complex systems, more complex from the thermal control viewpoint. Okay, so the bottom line is that all these all the controllers in the world won't help you if you are thermally unstable, because in a steady state, if you are actually dissipating more power than what you can reasonably drive out to the environment, then your temperature is going to go up. So there is no controller that will save you when you are thermally unstable. And so the systems that we design today, unfortunately, are more and more thermally unstable. And this actually means that these systems will never be able to work sustainably at maximum speed for a very arbitrarily long period of time, because they are not going to be sustainable. There is no controller that will help you doing this magic. So people are trying to say, well, what if we settle for something else? What we settle if for some capability of actually, most of the times your system will run in dark silicon mode, so with only few cores, so that it is sufficient. It can do some work, and this is going to be okay in terms of steady state behavior. But then sometimes we need a very high performance, and we do this on a very short time period. So it's like a boost mode or burst computation. And this is actually being called computational sprinting by the first people that explored this concept. And so how can we do this? How can we afford to do this? Well, the idea is that the system is going to mostly working in the dark silicon. Then we need a burst of speed. And your power in this burst of speed is very much above your thermal design limit. So you are running in a thermally unstable condition that will burn your system if you keep doing it. The whole trick is do it for a very short time before you run out of thermal headroom. And this is called a computational sprint. What helps you is if your system has some thermal capacitance, so it is able to store thermal energy for some time before the temperature shoots up. And in this case, you are essentially having is similar to a battery, but of thermal headroom, where if you have sufficient thermal capacity in your system, you can operate your system for a longer period at maximum speed, so that you can give the performance you need for a short burst, and then you go back into the average mode, where you cannot really afford to keep doing this short burst. And so the idea is that you would use your thermal capacitance of the system to afford short bursts, and then you will have some relaxation time where you have to bring back the energy into a normal envelope, so that you can sooner or later afford another burst in the future. Okay, so this is called computational sprinting. Now, this capacitance of the system, thermal capacity of the system, can be enhanced by so-called phase change materials. Phase change materials is a very fancy name for some material that would melt by absorbing the heat from your system. So, like there are several materials, some sort of a plastic or specialized material that have quite a large thermal capacity when they melt. So essentially you can have a layer of this thermal capacitance material on top of your chip before the heat spreader, and this will increase your thermal capacitance by a significant amount. This is actually a technique that has been used in various embodiments in real systems. Okay, for example, when they put a big metal on top of your chips, because this metal will actually spread the heat. But not only, it will take some time for this metal to heat up entirely. So you have some time before your whole system goes out of range in terms of temperature. But phase change materials increase this value. Okay, so in terms of various type of workloads, there is actually, mobile workloads are good for this type of sprinting behavior, because usually cell phones are compared by the time they take to launch an application or to recover a web page, and this is a burst of computation. You don't need to run sustainably for very, very long time. So this is actually a very good case where thermal sprinting would make sense. And in fact, a lot of the workloads are, in a sense, quality of service or user experience bound, and so being able to deliver this small burst is actually going to give a very good quality. So the idea here is that there are some applications that do need a very high priority because the experience of the user depends on this, and sometimes phones are used to do some very critical tasks, like measuring your ECG or doing something like that. But so let's say that there are mixed workloads where you have some applications that do need guaranteed bursts, so they do need a burst, but for a very short time, and some other applications that where to give them bursts is nice but not required. So it's some sort of a classification of applications, guaranteed application where you want to guarantee that the burst is available, and best effort applications where the energy burst may be available if there is some thermal headroom. So the question is that we looked into is how we can extend the baseline sprinting controller to have this guaranteed sprinting capability for some specific applications. Okay, so some sort of a real-time constraint in temperature. So the idea of the basic computational sprinting is actually, there are some technical details that we'll skip in the interest of time, but the idea of the baseline sprinting controller is very simple. It works like that. You have usually your system in with a large power buffer, and if you are sprinting, you are getting very high performance for a short time, which is until you exhaust this power buffer. And the system is based on, the controller is based on a threshold, and essentially it says, if someone asks me for a burst, I will give it the burst. And I will give it until the burst finishes, so the guy doesn't need any more the burst, or my thermal capacitance is filled up. And in that case, I will see that because the temperature of my system during the phase transition will stay constant, because it's like when water is boiling, you are injecting heat, but the temperature is not going up because water is boiling. So it's blocked the temperature, and then because of the phase change. And then when the phase change is finished, the temperature will start shooting up. So I have a threshold controller that when the temperature reaches again its is higher gradients, I will immediately put the system into safe conditions so that the energy can be recovered. So it's like a greedy approach to give all the burst that is needed when is needed to the first one that asks for it. Okay? So this is a simple reactive thermal control based on a threshold. It works very well, but it does not give any guarantee. So what we looked into is the resprinting capability. The capability of actually having the system that will be able to resprint. So to guarantee that some density of sprints is provided, so that if an application, a required application requires a density of sprints over time, some average, some minimum number of sprint seconds over a period, I have that. I can guarantee that this is there. Okay, so for that we actually use a two-level controller. A controller in the bottom that is actually the one that is controlling the temperature of the cores using scalable model predictive. And on top, we have this higher level controller that manages the phase change material in such a way that it will have this guaranteed resprinting property. Okay, and then of course the comparison has to be against the threshold controller. So again, the idea here is that I have all my 16 cores. When they are all running at the maximum, they have 1 watt of power dissipation. When they are running at the minimum, they have 150 milliwatts. So they have a range of operating conditions. And then when they are idle, they consume 50 milliwatts. And the total power in rest condition, which is essentially one core working and all the other core in idle, is fully sustainable. And the power when I'm sprinting, which everybody is running, is completely non-sustainable. Okay, so and I have a PCM material on top of the chip to enhance the thermal capacitance. So the model is the usual model, the silicon layer model with the thermal capacitance, the thermal resistance that model the heat conduction, and the power injection that is the heat dissipated by the transistors in the tile. And then you have the PCM, and in principle the PCM can be modeled by a very large capacitance and a resistance to the environment, which is the package, and this is the compact resistance that represents the thermal coupling to the environment. Unfortunately, this capacitance is not linear because of the phase change. When is, if we were a linear capacitance, it would not account for the fact that during the phase change, the temperature, you inject heat, but the temperature doesn't change. So this capacitance during the phase change becomes infinite, in other words. So this is a nonlinear model, and in fact, you see it in the temperature evolution during the phase change. So here is when your chip is heating up. It reaches the melting temperature of the PCM, then it is blocked at the melting temperature of the PCM until it melts. The whole PCM is melted, and when the phase change is completed, the temperature starts going up again. Okay, so this is clearly nonlinear. So, how do you do this? How do you handle this? Well, there are quite some complex equations, but basically you use a trick. So in this case, the temperature of your system is determined by the power, the injected temperature, the neighborhood transmitted power, and this is actually the power, the effect of the heat of the PCM. Well, let me skip in the interest of time, and so what the trick that we apply is that actually we are looking into the PCM internal energy. We are using the PCM internal energy to measure how far we are from heating up the entire PCM and changing the phase. So the more energy you inject, the more the phase change will go toward the limit. And at the end, when you have injected the whole energy that can be stored here during the phase change, your system will enter again into a linear phase where it will start going up with the temperature.
What will happen when the temperature is decreased?
Oh, yes.
After melting.
Yeah, after melting, what will happen is essentially it's like a reservoir. Will start to the system will start to gather energy, thermal energy. So essentially, the system will gradually, with its own time constant, will gradually go back into the solid state.
Solidification will start.
Yes. Okay, so this is actually where the nonlinear function is, and essentially this is actually showing the nonlinearity in the U energy versus temperature function in the PCM. So essentially this nonlinearity is handled by working into energy. Then to make the long story short, if you apply this type of control, then you can view your tasks in two groups, best effort groups, where they will get sprinting if there is room, and the guaranteed groups are guys that will get sprinting if they will need guaranteed sprinting. And what guaranteed sprinting means that we call it MN sprinting, where M is the minimum period and N is a maximum execution time. So NM guaranteed sprinting property is described here, and I think is better described by this picture, which essentially shows that over a period of M, you have to guarantee at least a duration of N sprint for the guaranteed tasks. Okay, so this is a really pictorial description of what we want to do. Okay, and so the idea of the controller, and with that we close for today, is the following. You know what is the maximum energy you can accumulate, you can take in when you're with your PCM. And so essentially you say, okay, I want to make sure that I will always have a reserve of energy enough to execute the guaranteed guys over this small time interval where all the sprinting guaranteed guys will have to fit here, because this is my contract with them. So I will take a reserve. So we say, okay, I will never go beyond putting so much thermal energy in the system that I will eat up these guys, this thermal energy reserve, for tasks that do not have a write for it. So I basically use a reserve here, and I will eat up this reserve only for the thermal guaranteed guys. And then, essentially, if I want to guarantee this, I cannot. I need also to make sure that if it has been used in the previous time step, I give enough rest time for this energy to be collected again, like in the energy reservoir, before the period ends and before the next burst is requested. And so this is the energy bound that my system has. And essentially what you want to do in your control is that you will never want to pass this green bound. And this green bound is what you can safely, the thermal capacitance, the energy that you can safely allocate to guys that are not guaranteed, and will still guarantee that the guaranteed guy will get what they have bargained for. So if your system goes into this mode, this is when you are eating up your budget because you are running in sprint. Then you are going here in a low requirement, and then you are, getting far from your bound. And then this is a guy that is not a guaranteed guy, and he wants to sprint. You are below the bound, so you give him the sprint. And you give it the sprint until your energy hits the bound here. The energy that you have injected in the reservoir hits the bound here, and then you cannot give it. But the guy would like more, okay? So your controller has to kick in here and put it into the state that will actually ensure that this bound is not violated. And the state is not necessarily the lowest power state, because still this guy can do something useful. As long as it doesn't go above this limit, you can allow it to work. And it's interesting to notice that the amount of work that you can let this guy do is actually a function of the ambient temperature. Okay. So it's not, and this is where intelligent control plays. Okay. So the way you implement it is a hierarchical controller, where you have a low-level thermal MPC and high-level model predictive controller. And not surprisingly, it works as expected, and it works, of course, better than the standard threshold-based controller. But I'm out of time, so I will stop here, and we'll move to a different topic when we resume. Thank you.
Take some questions on
If nobody is
questions.
Thank you for your speak. And in your previous slide, you show that the model used to compute the temperatures take only 3% or 0.3% of schedule.
Yes.
But in this case, what's your sampling rate of the power? The sampling rate of the power, because if the sampling rate of the power is very high, such that you use very high frequency power input, it will take very long time to compute out your temperature.
I'm not sure I understand, sorry.
Such as if the power input you use to compute the thermal, the temperature is such as 2 point of the power is between 1 microsecond, or between two input is 1 millisecond. Mm-hmm. What's the sampling rate of the power you use there?
Okay, so essentially the way, I'm not sure I understood the question, so I'll try to answer to shoot in the dark, but let's see, then we can take it offline. So essentially the controller is triggered on fixed time intervals, okay?
Yeah.
So when you trigger the controller, you sample the temperature, and you also sample the power. what sampling the power means is essentially that you will look into the, remember that we don't measure the power. We don't have a power measurement.
And what I mean is the interval of the sampling power. How long is the interval?
The interval of the sampling power at which we
schedule.
sample the power is the same that we trigger in which we trigger the controller.
But as I know, maybe it will have a very high variation in this interval.
This is true. This is totally true because the workload can change very rapidly. But remember that these are systems that are managed by, they're not, the workload doesn't come in like that. It comes in with the scheduling intervals. Okay? So we are aligning the thermal control to the scheduler. So the workload changes are on, can be only with internal to a thread, to a program. So a program may enter from a phase of low workload into a phase of high workload during a scheduling interval. And for that variation of power, we account for the total. So this is the average power that is dissipated in the previous time interval, okay, which is going to be taken as an input. And the way it works is that since we are sampling it at frequently enough to avoid to have thermal overruns in the sampling interval, then you can use the average power between the two sampling intervals and not worry about the variations of the power between the two sampling intervals. The trick is to sample fast enough, because if you would sample in every 10 seconds, then you will have a problem because you may run out of thermal room between two sampling intervals.
But if you sample in fast enough, it may be not only cost you 3% computation time compared.
Oh yeah, I mean, if you want to sample it at a nanosecond, then it will be, or 1 microsecond sampling, then your workload will be your controller will have to execute many times. If you want to be reactive, extremely reactive, you have some system where your thermal time constants are really small. I don't know such systems, but maybe there are. Actually, the complexity of this controller is such that you can implement it in hardware. You can have a hardware implementation of this controller, and this is actually what has already been done for power controllers. For example, Intel is doing it in hardware.
Okay, thank you.
So what remains of the model predictive if you do it for such a short time? Isn't it just standard bank control, or I don't know, I'm not a control person, but
okay, so I did not spend time in comparing the various control schemes, because this is, as I said, work that was quite old. So the quality of this model predictive control in terms of control metrics, quality like smoothness, mean square error on the tracking signals and so on, is definitely better than PID or bang and so on. Now, we also tried to forget about the complexity, extend the time horizon to see, if I have a very long time horizon, if it would work better than on a short time horizon, and it doesn't work very significantly better because of your not so good capability of estimating the future workload. So I think that the short time horizon is. And remember that you are revising it is a rolling horizon approach. So you have a little bit look ahead capability, but it's not magic. This is going to essentially be smooth. If you want to do longer term type of decisions, then you have to go into a different approach where you essentially would have to have a more discrete model, like an allocation model and so on. I will talk a little bit about that too, but. Essentially, my answer is it performs better than PID control, significantly better than PID control or on-off threshold-based control. But it's no magic, not 10 times better because.
I don't deny. I would not call it model predictive control. That's all. You invented a new method for controlling for the next step of the operation.
But, if you look at the literature model predictive control, most of the model predictive control are used like that. Not with extremely long time horizons.
There is a question over there as well.
So First of all, thank you for the interesting presentation. I would like to step a little bit back and ask you about the idea of sprinting in terms of one of the initial goals that you announced, reliability. Mm-hmm. So from my point of view, if you're running sort of at an average or a little bit below average, but constant load, you might experience less smaller wear out due to like particle transfer in very small electronic elements.
I think you are perfectly right. So there are two things about it. One thing is that one thing is that you are not. What really matters is the phase change temperature of your phase change material. Okay, so you are not forced to put your phase change material at the temperature with the melting temperature at the temperature is extremely close to the high damage zone. So you could put it at a safer temperature so that during the sprinting you are blocked at the temperature that is not very, very close to the thermal runaway. Okay, so still you are running at the high temperature because otherwise it would not make sense to have this. But it's you could choose it lower than a region where your wearability will go very, very rapidly down. So this is one way, but overall, this is a technique that is damaging against reliability because it pushes the system to run into very high temperature for a short times. So there is nothing. So what some people are saying, and it's a cynical view, is that you are not going to use your phone for more than 2 years, and usually people design ICs for a lifetime of 10 years. So if you eat up some of your thermal lifetime because of this, and your phone works better for 2 years, it's okay. Okay, but I would not use this argument for something that goes on an airplane or on a car. Okay, but
okay, thank you very much. And now it's time for lunch. I don't know is any other announcement from the.
For the poster presenters, these posters must be down in 3 seconds, please.